Hello. I know that sometimes just seeing solutions can be a little bit tricky to follow, so I thought I would make a couple of videos, see if I could help you guys out. These are some of the solutions from the Path to a 5 packet. In this video, I'm going to kind of talk about some of the limit things. So if I do take a quick look here, this is just your basic definition of limit stuff. Here, evaluating a limit, since this is a nice function, they were able to do it just by plugging in 3. And that's where they get the answer from. On number 2, things got a little bit trickier. If you try plugging in -2, you realize that you have an undefined situation. Remember that just because you have something over 0 doesn't automatically mean that the limit doesn't exist. Sometimes you can end up having a limit anyway. So what you can see them looking at over here is exploring what happens a little bit before -2 and what happens a little bit after -2. And what you end up seeing is the denominator changes sign, but the numerator doesn't. And so the result is we have a sign change and we have a sudden jump there. That's why it does not exist. Similarly, if you look at number 3, at B, we have a sudden jump. That's a problem for limits. There is no single value the function approaches. That's why it does not exist at B. At A, we don't have that sudden jump. We're approaching the whole from either side. So the value of the whole at 1 is the value of the limit. We don't have a problem there. If I move on to section 2, now they start talking about right and left-hand limits. So this allows us to start looking at limits of those kinds of jumpy things, because here, if we talk about the limit as x approaches 3 from the left, we know that we're getting closer and closer, staying right on that -5. But if we're coming from the right-hand side, that's where we're getting towards this 2. If they had asked the question here in number 8, what's the limit as we approach -3 without looking at a side, that's when we get does not exist. Okay. Similarly, actually a little bit differently, if I approach 0, you kind of see us coming in. We have that sharp corner. That's a problem for derivatives. That's not a problem for limits. So you see in number 3, we get -4 from the left. In 7, we get -4 coming from the right. In number 9, the limit overall is -4. There's no problems at all. Do make sure you're noticing for -6, approaching from the right, we're staying on this horizontal line -5. That's their answer up here. If I go to from the left, or rather they just ask about the entire limit, you might notice there is no graph to the left, so we don't have 2 sides for these things to work out with, and that's why they have a does not exist. Moving on, horizontal asymptotes and limits at infinity. The main thing you guys need to understand is that these are the same thing. If we have the limit as x approaches infinity and we get a number, that is talking about the horizontal asymptote. So a lot of those rules you learned in pre-calc are good. What you're really going to look at a lot is you're going to look at whether you have where the higher degree is. Do you have more powers on top, more powers on bottom, or are the powers the same? You do kind of see here, powers are the same, so 4 over 1 is 4. Higher power in the denominator makes the limit go to 0. Higher power on top made the function get very, very large, but negative because of this guy. Number 4, the square root of a square makes it kind of act like a linear function. So that's why this still counts as 1 over 1, my lead coefficients. And you kind of get the same thing going on with number 5. Although since this was as we approach negative infinity, things get a little bit funky because the top can go negative, but the bottom with the square root can't. So that's why we get -1 instead of +1. Moving over to the other two questions. Here, since we know the degrees are the same, we know a over 1, the lead coefficients, is our limit as we go to infinity, or the horizontal asymptote. That's how they know immediately a is 2. Vertical asymptotes come when the function is undefined. So that's where the denominator goes to 0. So we basically need -3 plus c is 0, and that's where we get c equals 3 from. All right. Similarly, on number 7, as soon as they start saying y equals 2 is a horizontal asymptote, e is exactly how we describe that. Sound good? Okay. Vertical asymptotes, we talked a little bit about just now. Those generally come from the denominator being 0, especially if the denominator goes to 0, but the numerator doesn't. 0 over 0 cases are a little bit different. Those are our wholes. But here we'll have a vertical asymptote at -5. Here, if you factor both sides, you guys see the t plus 2 in both top and bottom. So that's what you want to look for to tell you that there's a hole, and only -3 will be the vertical asymptote. When you start talking about limits for these things, you have to look at the one-sided limits. Here, as we approach 1, the numerator goes to 6, the denominator goes to 0. That creates that 6 over 0 is an infinity case, but since the 0 might be a little bit bigger than 0 or a little less than 0, we could potentially get positive or negative infinity. And that's why they have to take a look at the two one-sided limits and see what's going on with the graph. Somewhere in here, my screen stopped showing me my drawing tools. Let me see if I can get those back somehow. Sadly, I'm not sure what happened to my drawing tools there. But you're going to get one of those things where suddenly the graph goes up from one side and it goes down on the other side, and that's what's going to create this problem here. On number 5, since the denominator is raised to a 4th power, that denominator is always positive no matter what. And that's how we can go and get positive infinity on both sides. Continuing along, part 5 is about weird limits. I agree with their advice that you want to be able to visualize graphs of things. If you look at something like e to the 1 over x, you also want to be able to look at parts of things. 1 over something very, very large goes to 0. E to the 0 is 1. Here, we just talked about looking at degrees. This is getting very, very big or going to infinity. Tangent gets very big as you approach 90 degrees. Similarly, in number 3, since these have the same degree on top and bottom, we have this fraction goes to approximately 1. Natural log of 1 is 0. As we approach 0 from the left here, 1 over 0 will get very, very big, but also be negative. So we have e to the negative infinity, which is going to make this a very, very small number, hence the going to 0. Continuity, we've talked about as having no breaks, no jumps, so the limit has to exist and the limit has to be nice. So here, the lack of limit causes a continuity problem. Here, even though the limit exists, the value of the function is in the wrong place. That's why number 2 is bad. Number 3, even though the limit exists, the function itself doesn't exist. There's no point at x equals 2. We're missing answers on 5 and 6, and I am also missing my screen tools that were there at the beginning of this, and now they're gone. So you guys are just going to have to listen to me real close. Basically, for continuity, we want to make sure the branches of the function go to the same place. At -2, we're using one of these two functions depending on which side we approach from. So here, if I plug in -2 here, I get -13. And if I plug in -2 to the middle branch, I also get -13. That's good for continuity. If I try x equals 2 from one side or the other, plugging in 2 here, I get -13. Plugging in 2 to the bottom, I get +13. That's bad. That creates one of those big sudden jumps. So h of x is not continuous at 2. Similarly, for number 6, if we're going to have this function be continuous, we need to be able to see the function, the two parts matching. So if I plug in 3 to both sides, I'll get 3c plus 1 equals 9c minus 1. 9 because this says to do x squared. And then you can just solve that equation, and I think you should end up getting x equals 1, c equals 1/3, excuse me, as an answer. This is the last topic that I'm going to do in this video. This really starts blending more towards a derivative topic than limits, but it's still somewhat related. Rate of change, average rate of change is just our slope calculation. Excuse me. Average rate of change is our slope calculation. So let's just make sure that we're finding slope. We will turn it into a derivative by making sure the slope is over a very, very small region. So for number 1, we're just finding the slope between these 2 points, and that gives me change in y over change in x is bacteria per day. Similarly here, we're looking at the average rate of change over 3 minutes. So we looked at the values of the function at 3 and 0 and took that difference over 3. And finally here they start talking about derivatives, and we had said before the idea of derivative is that we're looking at slope but over the smallest interval possible. So here they show 2 possible answers as things that include 1870 over the smallest possible window. I would also consider it okay if you did the slope between the point at 1860 and the point at 1880. Since these are units in millions of something, and this is units in years, they did have units in millions per year. Do recall that we talked about being very explicit when you guys were talking about the meaning of things. So when you get that answer for the derivative, it means we're increasing, because the slope was positive, by this number of millions per year. Use the units and say that it's at time of 1870 so we know when we're hitting that slope. All of those are parts that the AP exam looks for in a free response question. If you guys have any other questions, as usual, please email me or post on the discussion board on Canvas. I hope you guys are doing well, staying safe and staying healthy, and let me know if there's anything else you guys need. Thank you and good luck.